Okay, so welcome back to the second of our two seminars today. It's a huge pleasure to have Roberto Oliveira with us today from IMPA, and he's going to speak about reversible Markov chains with non-negative spectrum. Over to you, Roberto.
So, well, thanks, Christina and Alex, for the kind invitation. It's a great pleasure to be giving a talk to you today. So this is joint work with Yuval, who I think is here. I think I saw his name. But this is work that somehow, okay, there'll be a combination of some new results, but mostly I'm going to be talking about new proofs of older results. And but the main idea is that somehow there's what I'd like to say is a nicer approach to these things, and that, I mean, in many cases this approach gives us sharp results, and I mean, there are many other results that are scattered in the literature that we somehow managed to give unified proofs for. Okay, so, but let me try to at least explain the title of the talk before I get started, right? So, well, Markov chains I'm guessing that most people in the audience, I mean, I quickly went through the names. I'm guessing that most people know what they are. But well, in case you don't, it's just talking about, and maybe I'm gonna fix notation right now. There's something called the state space. And there's a process, right? This for us is always gonna be finite. It has n elements. And then there's a process in discrete time with values in omega. So let me maybe try to draw omega here. And okay, so you have a bunch of, well, let me actually call them, yeah, omega 1, omega 2, here's omega 3, omega 4, omega 5, and so on. So this process, okay, let's say that it's here at time 0. And what defines a Markov chain is a so-called transition matrix that gives you a rule for computing your probability of being at another stage in the next time step, right? So maybe the probability that it jumps from the one state to the other is P of omega 1 and omega 2. And then for any pair of states, right, you have this matrix. Well, it's a square matrix, but I label its entries by the points, by pairs of points in omega. And this matrix gives me, right, so it gives me probabilities. So all of these entries are non-negative. The rows add up to 1. And that's what the matrix is telling you. So if you happen to be at x naught, your chance of, right, at x naught is equal to omega 1, right? So if x naught happens to be at omega 1, and you want to know your probability of jumping to omega 2, that's P of omega 1 and omega 2. So the next jump, you happen to be at omega 2, right? So maybe this is x1. And you want to know what your probability is of jumping from omega 2 to omega 4. And that's omega 2, omega 4. And maybe, so now you're here. I'm going to be a bit more formal later. But in any case, so that's the idea, right? So in any case, the chain makes a random choice that depends on its current state and nothing else, where it's going to be next. And the way you make the random choice is that if you're at omega, your chance of jumping to omega prime is P of omega, omega prime. So that's a Markov chain. And we're going to be interested, okay, so as I said, I want to explain the title, right? So at least hopefully now you know what a Markov chain is. And now we're going to explain what reversibility means. Well, reversibility is a property that a chain may or may not have, right? So right here, reversibility. And well, we're giving a vector, I'm going to call a probability vector or a probability distribution if you want an omega, right? So, and again, that means that it has no negative entries, and they sum to 1. And we say that P is reversible with respect to pi if pi of x p x y equals pi of y p y x for all x and y and omega. So again, this is a property that a chain may or may not have, right? You define reversibility with respect to a reference probability measure. When a chain does have this property, and we're going to see examples where it does, I mean, natural and interesting and important examples where it does. When it has this property, then you gain suddenly a lot of information about your transition matrix, right? This matrix P here. And the main thing for us is that, well, P has a real spectrum. And maybe the reason for this, for people who don't know, will going to become clearer pretty soon. So when you have this, well, P has real spectrum, it's diagonalizable, right? So it has a largest eigenvalue, which is always equal to 1. And the eigenvector is the all ones vector. And it has a bunch of other eigenvalues. And well, the smallest eigenvalue I'm going to talk about later, it's always greater than -1. But in any case, you begin to see that, well, this condition, the way you're going to make use of it, reversibility, it's because, well, it's by way of the spectrum of P, which is going to be important for us. Maybe it's not clear yet why the spectrum matters, but it's going to become clear later on. And if you want to give a probability interpretation to this condition, it just means that if you take x naught with distribution pi, and x1 is just a jump according to matrix P, right, from x naught, right? You just run the Markov chain the way I described. So each step, you choose your next position according to P. So reversibility means that the distribution of this process going forward is the same as it going backwards in time, right? So that's where the name comes from. Right, so now I can explain the title, right? So you know what Markov chains are, you know what reversibility is, and reversible Markov chains with no negative spectrum are reversible chains that therefore have a real spectrum that only has no negative eigenvalues. Of course, you may ask, well, why is this important, or what examples, interesting examples of this? Perhaps the nicest example, which you should keep in mind because it's going to be important for us, is lazy random walk on a graph G. So here the state space is a set of vertices of a graph G. I mean, I'm not going to be very formal about what a graph means, but so here I have some graph, I guess. This is a planar graph, but there's nothing to that. And the lazy random walk is a process where your transition matrix is like this. So if you're sitting at a vertex X, the probability of jumping from X to X itself is a half. Probability of jumping from X to Y is 1 over degree of X, right? So dx is number of neighbors. And this is if Y is adjacent to X, right? So for instance, this Y here is a neighbor of X, so it has probability, well, let me count the degree. 1, 2, 3, 4, I guess degree 6 here, so it has probability 1 over 12. If you're at X, you have probability 1 over 12 jumping to Y. And if in all, right, so you have a probability of staying in place, a probability of jumping to each neighbor, and all other guys you have no probability of jumping to. So this random process, what it does is, well, it starts from somewhere, let's say X, and then it jumps to a certain Y, which is a neighbor, and maybe in the next step it stays in place, right? So first jumps like this, second jump stays in place, third jump either stays in place again or jumps to a random neighbor, let's say it jumps over here, and so on and so forth. And this is a very, well, as I said, it's an example of a Markov chain that has no negative spectrum. You could consider a related process where you have no probability of staying in place. You just jump to a random neighbor with equal, right? So any random neighbor with equal probabilities. That's the standard random walk, but that doesn't necessarily have no negative spectrum. For instance, if you take a bipartite graph like this, it's very easy to show that for such G, the smallest eigenvalue so is -1. So this is bad for us. Right? The lazy random walk is always good. It has no negative spectrum, always. And it's always reversible. And by the way, what's the stationary measure, right? So what's the pi measure that's reversible with respect to? Well, it's just degree divided by the sum of degrees, which is just 2 times the number of edges in the graph. Right, so this is one example of reversible Markov chains with no negative spectrum. Reversible chains abound. So for instance, and when you do Markov chain Monte Carlo, you want to design a Markov chain that has pi of the stationary distribution. A way of doing that is just ensuring that the chain is reversible with respect to pi. Right, so that's one example. But there are many examples for statistical mechanics, such things as Glauber dynamics for the Ising model, hardcore model, all sorts of statistical mechanical models. Those are all reversible. And so there are many interesting chains in this class. Or I mean, I'm not going to write them all down, but or not even the names. And I mean, there are many interesting examples of reversible things. So. And if the chain is lazy, so meaning that if the probability of staying in place at least a half for all x, then you're guaranteed to have no negative spectrum. So that's very easy to prove. And that means that, you know, if you really want your chain to have no negative spectrum, what you've got to do, instead of just running it in the sort of plain vanilla version, you at each time step, you flip a coin to decide whether it's going to move or not. And if it does move, you move it according to P, or to your original P. So that's kind of making, you can make any Markov chain lazy by this trick. And so my goal today, right, so is, well, consists of maybe 3 things. So first of all, I mean, what can you say about reversible Markov chains with no negative spectrum? And that's, of course, a very general question, but we're gonna, so first approximation, or at least kind of at first, we're gonna be interested in results having to do with the spectral gap of P, which is just the difference between the largest eigenvalue and lambda 2 of P. I'm gonna argue in the next slide that this, for interesting example, is no negative, or sorry, it's positive. Right, so I want to get sharp bounds on the chain. I mean, all sorts of properties I'm going to discuss in terms of just by knowing that this is a reversible Markov chain with a negative spectrum with measure pi, right? This measure that I define with respect to pi, and I have a positive spectral gap, a certain value. And then we're going to look, okay, but this is very basic information. Perhaps you know more about your chain, right? So you don't simply know that it's reversible, it has a certain spectral gap. So we're going to be looking at improved results, especially in the graph setting. Yeah, so for lazy random walks. And perhaps I can summarize what I'm going to show later as follows. So for we're going to prove a few bounds that are sharp if you're in the class or reversible Markov chains in a negative spectrum, meaning, I mean, this is sort of the best possible bound you get just with this information. And but then in the graph setting, we're going to be able to improve some of these bounds and say, well, actually, if you know you have a graph, then you can do better, right? By using things that are specific to graphs, of course. And as I said, I mean, many of the results I'm going to be talking about are known, a few are new, and I'm going to try to make sure that you know which is which as I go on, right? So, okay, what kinds of results I'm going to be talking about? So, first, okay, so. And, okay, so if I have a subset of the state space, let's say it's non-empty, I can look at things, or I can look at this hitting time of A, which is just the smallest t, such that xt belongs to A. Under certain assumptions, this is almost really finite, and the assumptions are going to come later. And you can ask questions about how does this thing behave when t is large, or maybe for any fixed t, right? So you want to know things about this, about something like this, or maybe you want to know things about the distribution of tau A. And maybe I should mention, I mean, I didn't define the symbol yet. This thing here means that P is running, right? The Markov chain P is running with initial state sampled according to this measure pi. And we're going to be interested in distribution of tau A, especially in the setting where the time to hit A, the expected time to hit A, is much larger than the inverse spectral gap, which is sometimes called the relaxation time. And here we're going to be discussing some old results of Aldous and Brown. So there are known results, and continuous time, we're going to find discrete time versions. And we're also going to be talking about a variant of this thing, which is when I have a sequence of subsets, and let me call this a script A, and I define tau script A as the infimum over such that xt belongs to A sub t. So now you have a moving target, right? Hitting time is talking about how long do you take to hit a target. Now the target is moving. We're assuming that it moves deterministically, but then we can also look at what happens when it moves randomly. And then, so one natural question, how do you quantify, what can you say about this tail bound, right? So how long does it take until you hit a moving target? And especially, how does it compare to hitting static targets, right? So maybe the worst possible moving target, the target that's going to take you the longest to hit, doesn't take that much longer to hit than the worst possible static target. I'm going to be seeing things to that effect. And also, we're going to be looking at things, okay, okay, I guess it's two versions of this. So deterministic A, and also the case where A itself is a Markov chain. And in this case, they're old results of Aldous. You're going to, I guess, you'll hear his name a few times in this talk. I think this is from 91 AAP. So there's one class of results, and there's another class which I'm also going to spend some time on, which, okay, this is a hitting time kind of results. And then there are results about concentration, where I'm going to be looking at random variables like this. So it's just a sum from times t equals 0 to n. of ft max sub t. So at each time step, I have a function going from the state space to R. And so, I mean, the function could be different, right? And I want to look at things like, well, it's a probability that Sn minus the mean of Sn is greater than some lambda. And we're going to get bounds in some sense sharp or best possible under our assumptions when the functions are all equal. And there's a third thing that I'm not sure I'm going to have time to get into, and maybe I'm just going to draw it right now, which are intersections. And intersections are just like you take two independent Markov chains, or maybe with the same underlying law. And starting from different points in your state space, and you define an intersection time, which is just the infimum smallest t, so such that exists S1 and S2 less than t, that the chains intersect, right? So how long do I have these to run these chains until the paths cross? So this, I really don't think I'm gonna have much time on this. So okay, hopefully the goals are clear. And I'm gonna start by jumping into the subject of hitting times. And I mean, the things that are gonna come up are gonna be useful later, right? So let me first, yeah. So let me say a few basic things that are gonna. Right. Remember, I have this assumption that the spectrum, right? The assumptions imply that the spectrum of P is real and non-negative, and I'm assuming that this difference here, right? I want to assume that this difference here is positive. And so this positivity condition here, it's sufficient to ensure that this chain P converges to a stationary distribution. What do I mean by that? Right. So I mean that if I look at a process, if I look at the position of the process time P, so here I'm saying I start the process. I start from X and I want to know my probability of being in Y. Well, some linear algebra really tells you that this takes the form of power of T. So that's how T comes in. And it's a theorem that this thing here converges, well, to the stationary distribution, which in this case, remember, we're thinking that P is reversible with respect to some probability measure pi. So there are many things going on here. First of all, well, we have a limit. Second, the limit does not depend on the initial conditions. So I could start from a deterministic state or any state any random state in my state space, and the limit would be the same. So the chain sort of forgets where it started from. And it's also because Markov chains sort of don't have a memory, right? So this thing here is going to imply that all Y in the state space are hit infinitely many times. Or if you want to say, well, the chain is recurrent, right? The state space finite, so that's not very surprising. But in particular, this means that for any non-empty set, right, tau A is almost surely finite, so this hitting time is finite. Now, there are all sorts of questions you can ask about this sort of convergence, and I'm a big fan of such questions about so-called mixing times, right? The time it takes you to actually forget to a pre-specified error where you started from. I'm not going to get into that right now, so maybe towards the end I'll say a few things, but one thing I should say is that if you want to measure how fast the convergence happens, this has a lot to do with the spectral gap. Right? So in many analysis of Markov chains, one of the very first things you do is to estimate the spectral gap, and there are many tools for that. So canonical paths arguments, comparison arguments, all sorts of things are specifically developed because this problem of bounding the spectrum or bounding the spectral gap is very important. And that's one reason why you might want to study things in terms of the spectral gap. And let me actually introduce a piece of terminology that's going to be useful later. I'm gonna a pi gamma chain for me is a chain that has no negative spectrum, has reversible measure pi, and has a gap of at least gamma. And so let me jump to hitting times now. And I still need to define one more object, which in some sense is the simplest possible chain with a spectral gap gamma. And I'm gonna, where gamma xy, well, I is the identity matrix, of course, and this capital pi here is just a matrix that jumps to the stationary distribution in a single step. So this thing here for me is going to be the extremal, well, for reasons that are going to be clear soon, right? So it's just a calculation to check that, well, you look at the eigenvalues of this matrix, the vector 1 is sent to itself. Any vector orthogonal to one itself is sent to 1 minus gamma times itself. And oh, sorry, yeah, I should say what I'm saying orthogonal here, but I really need to define the inner product at some point. So I'm gonna define this for functions f and g going from theta to r. I'm gonna define this inner product by like this. Right. And I'm going to notice that any chain that's reversible with respect to pi is actually self-adjoint for this inner product. So which is fpg pi equals pfg. And by the way, if you want to know why p has a real spectrum, that's one way to prove it, right? So you have a self-adjoint matrix or in some inner product and you use the spectral theorem, right? So not only it has real spectrum, but it has an orthonormal basis of eigenvectors. So it's diagonalizable. Right. So I have this extremal chain. Well, I mean, it's extremal for reasons that are going to become clear later. It's basically the largest possible pi gamma chain in the order given by this positive semi-definite relation. But it's also the simplest possible chain. I mean, what does this guy describe? It describes a chain that each time step flips a coin with probability 1 minus gamma, it stays in place, and with probability gamma, it jumps straight to the measure pi. So of course, there are many explicit things that we can compute about this. And let me state a theorem, well, the first parts of which are kind of obvious, but they're a good warm-up, perhaps. For all gamma f, for all pi, I mean, I'm not going to say for all pi, I guess. Okay, first statement, which I said is obvious, but it's kind of structured to prove. P pi tau a less than tau is maximized by the extremal chain overall, right? So over these pi gamma chains. And as I said, it's really not hard. It could be an exercise in the class, but it's instructive because an example of the kinds of things we're going to be doing. Second is there exists a probability measure, right, for any p. And now, let's say, per measure, or probability vector really, over gamma, such that the expectation, if you start from this measure, the expectation of tau A is a number 1 over PA, and we have the following bounds. So P pi tau A T is less than, I guess, pi of A complement 1 minus PA to the T, and below you have a similar thing, but 1 minus PA divided by gamma. And this is the non-trivial part somehow. Okay, the upper bound is not that easy either, but well, it's pretty easy actually, but not obvious. But the lower bound is really the special result here. And you can write this, if you like, as a relaxation time with the inverse and spectral gap divided by the expectation of tau A, because, well, almost, right? Yeah, I mean, up to a small error. And this is saying basically that if you take a long time to reach tau A from this special measure, right? Which, and by the way, we're going to show that this is larger essentially than the expectation for stationarity. Sorry. So if you take a long time to reach the set tau A, then the distribution of tau A, right? If you take a much longer time to reach tau A on average than your relaxation time or your inverse spectral gap, then the distribution of tau A is almost geometric, right? It's almost a geometric random variable with probability PA of success, right? So geometric, remember, is when you flip a coin, right? You flip an independent coin with probability PA of success, and you wait until you get your first heads, right? Your first success. And actually, you can strengthen this with a little bit more work. It's really nothing to say that the distance in total variation, if you know what this is, of the law of tau A when you start from pi, and the geometric random variable with success parameter PA, this is less than PA over gamma. And items 2 and 3 are this old result of Aldous and Brown that I mentioned, but they did things in continuous time. So I think this is the first result in discrete time for this problem. And somehow I think the proof is also easier, though of course that's a matter of taste. And you know, I found this proof, Yuval, so it's easier for me perhaps. So okay, let's look at number 1 because we're gonna, I mean, perhaps, well, the 3 parts are kind of important, but number 1 is the one that we're gonna use later when we talk about concentration. So yeah, first thing, how do I prove that it's maximized, right? Let me do a very simple calculation. So let me define a diagonal matrix that basically kills everything that goes inside A, right? So what are the diagonal entries? Well, they're 1 if x belongs to A complement, 0 if x belongs to A. Okay? So if I look at this guy, what is this? This is a sum over paths where no vertex belongs to A of just the probability of taking that path. So you have pi of x0 product from I equals 1 to t, p of xi minus 1 xi. Right? Why is that? So it's basically saying, well, if in order for tau A to be larger than t, it means that from time 0 to time t, it cannot have stepped on A. How do you write that probability? Well, you have all possible paths to the chain might take, right? These choices of x0 up to xt. How do you compute the probability? Well, the probability of starting from x0 is your starting measure. That's pi by definition in this case. And now you know, well, if you happen to be x0, your chance of jumping from there to x1 is p of x0 x1. And then your chance of jumping from x1 to x2 is p of x1 to x2, and so on and so forth. So that's how you define things in Markov chains. And of course, this is one way of writing it. Another way of writing it is use sum over all states, but then you sort of kill trajectories that ever go inside the set A, and you can do that by using this diagonal matrix. Sorry, let me move this a little bit. And now you can look at what happens. So remember this inner product that I defined. You just go back there and you can convince yourself, I think easily, that you have the following formula. P d to the t d1 pi, where 1 is just the all ones vector, or the all ones function. You need to write this down carefully, perhaps, to see that that's true. But that's just linear algebra, so maybe I don't want to explain too much. It's just saying, well, okay. I mean, basically, what I'm saying is that the non-trivial content of this is that this expression here has to do with the powers of dpd to the t. Well, not, sorry, to the powers of dpd. So it basically comes from dpd raised to the tth power. So, okay, what do we do with this? Well, okay. One thing you can say is that this thing here is at most, well, the L2 norm of this vector squared times the operator norm raised to t. And operator norm, I remind you, is right. So the operator norm of a matrix is just the sup of the norm of MF, where in this case, this norm defined by pi, right? Defined by this inner product that I chose. By f, where f is a zero function, right? The one function from omega to r. So this is just kind of standard stuff that you do. And okay, but now comes the, right? Remember, I want to prove that this is maximized when I take this special chain, right? Now, P has eigenvalues and eigenvectors. Okay, there is eigenvalue 1 with eigenvector equal to 1, the all ones vector, right? Because we know this is kind of trivial. Then there's the second largest eigenvalue, and this has an eigenvector that's orthogonal to 1, lambda 3, p, and so on. What about p star gamma? Well, it's it has a spectral decomposition as well, which gives me 1 with the same eigenvector. And now everybody else has, everybody that's orthogonal to 1 has an eigenvector 1 minus gamma. And I can use the same basis that I used above, right? Or maybe call, yeah, the same basis, right? There's a theorem that says that when you have two matrices like this, it's actually kind of a triviality, really. When you have two matrices that can be diagonalized in the same basis, and the eigenvalues of the first one are always smaller than the eigenvalues of the second one, then the second one dominates in this partial order, which is well, let me say, because right. So, and why does it dominate, by the way? Remember that I'm assuming that P is a pi gamma chain, right? So the second largest eigenvalue is at most 1 minus gamma, and the same is true of all the other guys, right? They're decreasing order. right? So I'm assuming that gamma p, which is 1 minus lambda 2 of p, is greater than gamma. So if I look at this, what I get is that for any function f, I mean, this is where this sort of partial order is coming from. For any function f that I take, if I look at it in a product like that, this fpf, this is less than or equal to fp star f prime. You just look at the composition. And also, if you put a diagonal matrix here, just like the diagonal matrix I defined, this still holds. You can just move the diagonal matrix around and notice that this is right. So for instance, this guy here is df times p times df pi, and same on the other side. Sorry, this is this. So if you have an expression like this, here's another thing from, well, matrix analysis, spectral theory, whatever, right? The largest eigenvalue of DPD is just the sup over vectors with norm 1 of an expression like this. And this, of course, is going to be less than the corresponding sup for D star. And it turns out, because we have matrices with no negative entries, this largest eigenvalue equals the operator norm. So this is another lemma, if you like, or I don't know, if you want to, from Frobenius theory, you can prove it with your bare hands. It's not really complicated. So now I can go back and basically finish the proof. Remember, I had this expression. It turns out that we just showed that this is less than dp star gamma d raised to t operator norm. And then if you look at what I got right now, this norm of d1 squared times this is exactly equal to the probability that this extreme will chain, right? So it satisfies this. So you have to check it yourself. And then you get this. So that's how you prove item 1 here. It's sort of a minor result, but I mean, it's nice, right? It has an explicit formula then, because the maximum is going to be, what's the probability? Remember, there's a chain that starts from pi, and at each step of probability gamma, it jumps to a state distributed according to pi. Probability 1 minus gamma stays in place, right? So what's this maximum? Well, at time 0, you have chance pi of a complement of missing a, and then you have to miss it another t times, right? And then this is the probability, right? The chance that you hit A in a step is the chance that if you haven't hit up to now, you have to decide to jump. So your coin has to come up heads, that's gamma. And then you have to jump to A. So this is the value. No big deal perhaps, but it's kind of nice. So it also gives information about the largest possible expectation for pi of A. Well, there's going to be 1 minus pi of A divided by gamma pi of A, but that's perhaps not important. So let me briefly discuss part 2, because this is going to be also important for things that come later. Okay. Part 2 is this. So now I have to look, okay, I have this probability, which I think I convinced you that that takes this form. Or at least I kind of scared you into believing that it takes this form. So Christina is giggling nervously. It means she's scared. Yeah. No? Good. Right. So again, I can right, I can bound things like this. Now I don't want to take a bound that's like the worst possible bound or the largest possible bound over pi gamma chains. I want to do something slightly different. I want to notice that because P is positive semi-definite, the same is true of this matrix. Again, it's just a trick of looking, right? So I want to say that this matrix has a non-negative spectrum, and for that I need to show that f, d, p, d, f is always greater than 0. And as I noticed before, that's something like p, d, f, right? Because p has a negative spectrum, the same is true of this guy. So maybe let's erase this. Yeah, sorry. And the spectrum of this guy consists of one larger eigenvalue, which it hasn't been non-negative and it's less than 1, just because the rows of this matrix, not all of them add up to 1, so you cannot have an eigenvalue equal to 1. And then you have some other eigenvalues here. And then you have your eigenvectors, and I'm going to call them phi 1, phi 2, and if you want, they are orthonormal eigenvectors. And there's a bunch of things that you know about phi 1. Perhaps the most important of them is that if you define a measure, if you define a probability distribution like this, well, okay, there are two things, right? So phi 1 is non-negative. That's just so-called Perron-Frobenius theory, right? A matrix of non-negative entries has to have the largest eigenvalue corresponds to a non-negative eigenvector. Well, it's non-zero either, so I can define this probability measure here, mu of a of x, and it turns out that mu of a is quasi-stationary for x. So what does that mean? It means this. So if you start the chain from mu a, and you ask, what's the probability that I have not hit a at time t, and that I happen to be in a state x. So this probability is 1 minus pa the t mu a of x. That's just a matrix equation right now. So what does that mean? Well, first of all, it means that if you start from ua, right? So what's the probability of tau a being greater than t? Well, it's going to be 1 minus pa raised to t. So from mu a tau a is a perfect geometric random variable. So there's a quasi-stationary distribution. Hopefully the terminology is clear. It's just, well, it's almost like a stationary distribution, except that you have this 1 minus pa, right? So you have this, and conditionally you're not hitting a. If you start from ua, you stay there forever. So that's the quasi-stationary. And right, so basically, if you look using the fact that the matrix is non-negative, remember, okay, what did I get from this? I got my upper bound there. So this d1 should be squared. So I had an upper bound d1, if you look at it, it's just phi of a complement, 1 minus pa to the t. Now, because I'm dealing with non-negative matrices, I can use the same thing to get a lower bound. The lower bound is, you just look at the spectral decomposition, ignore everything except what corresponds to the largest eigenvalue. And you get something like, well, the same d1 that we had before, times phi 1, pi squared, right? And this is really, well, we can show that phi 1 is supported on the set A complement. So basically, you can show that this thing is exactly equal to, so this guy. And now if you get a lower bound for this, you get a lower bound for this probability of not hitting A. And how do you get a lower bound for this? Well, basically you use the fact that you use two things, right? So okay, let me say it like this. First, you can look at this expression, and it's a consequence of the spectral decomposition that this takes the following form. It's just phi 1 1 squared plus 1 minus gamma norm of phi 1 squared minus this guy. And this is just saying that Markov chains with a positive gap they contract all vectors that are orthogonal to the all ones vector. But on the other hand, we know that this thing here, you can relate it to the right. And by the way, because we are normalizing the eigenvectors, this is 1, right? And because you can use the relationship with the quasi-stationary distribution to show that this actually, I mean, this is more or less the same as 1 with an error that's going to depend on PA. So perhaps I'm not going to be very explicit here. So by using these things, you can show that phi 1 times 1 is not too small, right? So here you see I have something like gamma times phi 1 minus 1 plus 1 minus gamma 1. You can show that phi 1 is not too small here. So you get a bound that's 1 minus PA. Let's see the bound that I claimed before, but I'm not going to give many details on that. And sorry. All right, so what have we accomplished? Well, we have sort of proven this theorem, the three-part theorem. Part 3 I haven't really described, but once you have parts 1 and 2 in the way I showed you, then it's just a matter of showing, well, the quasi-stationary distribution is almost the same as stationary distribution. Therefore, starting from UA, which gives you a geometric, is not that different than starting from pi. Okay. But I hope that my sketch gave you kind of a sense of what goes into this proof, which is, I mean, you really have to use the fact that you have a non-negative spectrum and a spectral gap and everything. So this has been a bit slow, I suppose. So I'm going to be a bit faster with the other things, a bit more impressionistic. So let me say about a few things about what happens with moving targets. And this, I guess, I called originally the meeting time lemma, but remember, I'm looking at the sequence of sets, and I want to know how long it takes until I hit one of these, right? And it turns out that just by using these spectral techniques, you can prove on the quality of the following form. S equals 1 to T, 1 minus P A sub S times pi of A0, pi of AT. And the proof of this is very simple. It's just showing that this probability here is something, right? So remember that I defined a diagonal matrix for a set A. So let's imagine now that I have a diagonal matrix defined for each set. So diagonal matrix of A0 is D0, diagonal matrix of A1 is D1. So if I write this probability matrix form, I get something like this. And everything times dt and 1 pi. Then I can take operator norms, but now it's convenient to break these terms here. So notice that I have something like d0 times the square root of p times d1. Square root of a positive semi-definite operator, an operator with positive spectrum, you just take the square root of the eigenvalues and keep the eigenvector, right? So you can use the operator norm all over the place, and all you have to realize is that the norm of this guy, for instance, is equal to the square root of the norm of d1 p d1. So the norm of an operator is the square root of the norm of the product of its transpose with itself, or its adjoint with itself. And then you get this. And this way, in the previous proof, related to some parameter having to do with the set A1, which is PA1. So you get a formula like this. So this result, I mean, there's a version of continuous time that I proved maybe in 2012. Then another paper with Yuval, we proved the version of this when instead of hitting sets, you have hitting points. And that was 2019, I think. But now we have a nicer proof somehow, with something much more general. And that brings us to an old result of Aldous, which is a very weird proof. I mean, to my mind, the proof's very weird, but it's very nice. I mean, like many other things that he's done. There's 93 AAP, which is you take two chains. Let's say they start from a stationary distribution, right? And P is still a pi gamma chain. So he proves in continuous time that the meeting time of these guys, what is that, right? So the time it takes for the two to be equal. Sorry. And he proved that the expectation of M, remember the two are starting from the stationary distribution. This is less than a really, really weird formula, which is a harmonic mean. Well, there's a constant here, or maybe 67 is a constant, I don't remember. Pi of x, expectation from pi of the hitting time of x, maximum of that with the mixing time, which we're not even going to try to define. It's a weird bound, and he claims it's probably sharp because it works for the star. He had a worse bound for more general graphs, and then he said, well, that bound doesn't work for the star, but if we look at the proof and tweak it a lot, we get this. So it's probably sharp, right? I wouldn't go as far. The nice thing is that when you're starting from the stationary distribution, well, he proved things for arbitrary initial points. We can do a little bit better when we start from the initial distribution by taking here 1 over gamma, which for people in the know is the lower bound for the mixing time. And then you can do things when you start from arbitrary points and you recover his bound with a better constant. And that combines the stuff that I just showed you, right? You can always look condition on one of the chains. You're sort of one chain trying to avoid the other. And then it can use that with something else that's related to Chernoff bounds, which maybe how much time do I have? Maybe 1 minute. Yes. Okay, good. And yeah, I'm not going to get even half as far as I thought, but it's okay. Yeah. It's the first time I give this talk, so if I can use that excuse. Right, so let me quickly say a few things about Chernoff bounds. And let me stick with the simplest setting where you're trying to look at something like you have a fixed function and then you're subtracting x expectation. And you want to know what's the probability that this is larger than some delta? Well, again, for people in the know, the first thing you do when you want to compute this is you find this function here, which I'm going to call pi fn of theta, which is the log moment generating function of the sum. Right? And you do tricks with this. Theorem. Pi of fn divided by n plus 1 theta is maximized, right, overall over pi gamma chains and over n. It's maximized by, okay, it's, yeah, not, let's say this is bounded over n and over pi gamma chains. It's bounded by a quantity here that I'm going to define, has a very explicit form, which comes from the extremal chain, which is just a limit psi f and theta my known star for the extremal chain. And this guy has a very simple form. It's the only root of the following equation. And this, yeah, so this, you take a stationary point, you subtract this psi f, no, sorry, phi f, and you're raising everything to a time g, 1. So x0 here has distribution pi, of course, and g is just a geometric gamma. And they're independent. So yeah, so by using this extremal chain and some calculation have to do with eigenvalues of all these things I showed you, you can find an exact form for the for the log moment generating function in this kind of soup sense. And then you can recover all known bounds for these guys, all Chernoff bounds from Markov chains literature, and you can prove some new results. They're like Bernstein bounds. So you can prove things that say like x minus lambda 2 divided by sigma squared gamma times, sigma squared and divided by, and there's a gamma and there's a constant as long as lambda is not large enough, not too large. Yeah, and I think I've run out of time, so thanks for your patience. And maybe I can, if you want to know about the other things, I can give you some hints in the answers to your questions.
Thank you for a very clear and beautiful talk. I'd like to invite people to ask questions. Can you either raise your hands or type in the chat that you'd like to ask, and I'll unmute people. And perhaps I can kick off with a really stupid question, which is, reversibility plays a sort of fundamental role in these results. What can one do without it?
Well, I guess you'd have to ask William, who gave a talk about that subject. So, so here's one very simple thing that we cannot do, right? So here, as you can see, many things are related to the fact that there is this extremal chain. Well, it's the extremal chain in the sense that it has the largest transition matrix according to this positive semi-definite order. And therefore, any expression like diagonal times p times diagonal, the norm of that is maximized by an extremal chain. And you can use that because the chain is very simple. So as far as I know, there's no analogous object in the realm of not necessarily reversible chain. So if you wanted to do something like this, right, maybe if you make the chain lazy, you can guarantee it has a negative spectrum, regardless of whether it's reversible or not. You cannot guarantee that the eigenvectors are orthogonal, but maybe that wouldn't be so much of an issue. But really, the kind of one crucial thing that's missing is an extremal chain in this sense. So, and I mean, there are things, there are results related to these things that wouldn't be true without, if you're talking about general Markov chains. So, in some sense, reversibility is a necessary assumption. We just know the extent to which it's necessary, or kind of how bad the bounds could get if you allow for non-reversible things.
Thank you. Anybody else have any questions? I know we're a little over time, but feel free to ask now. Raise your hands or type in the chat if you have a question. I can't. Oh, here's one. Okay, who's that? Ganesh. Okay, go ahead, Ganesh, if you want to unmute.
Okay.
Yep, we can hear you.
Yeah. Hi. Yeah, I had a quick question. Is there an analog for reversible continuous time chains? Is there an extremal chain?
Yes, so it's the same chain, right? So, but you run it. Okay, you have to be a bit careful, because when you're talking about continuous time, you can always sort of speed up the chain indefinitely, right? By multiplying the generator. So I have random walk on the graph at rate 1 and at rate 2 at rate 1,000, right? But let's say that you know your chains are running at rate 1, right? So it's you have a Markov chain P, but you look at what Aldous called the continuized version of it, where you at rate 1 you take a step according to P. Then it's the same chain. It's the same extremal chain.
Thanks. Yeah. Okay. Thanks.
No problem.
Anybody else? I can't see anybody else. So what I'm going to do is stop recording.